C-Therm's purpose is to simplify thermal conductivity testing for the materials of tomorrow. Since 2007, we have emerged as the global leader in test instrumentation. Our core strength in thermal conductivity is built on now industry standard Trident instrument and broadened through strategic partnerships with Rigaku and Metrovid, providing one of the most dynamic portfolios in thermal and mechanical analysis.
Thermal conductivity describes a material's ability to transfer heat energy through conduction. In electronics, whether you're developing a smartphone, aircraft, or electric vehicle battery pack, the thermal conductivity of the materials is a major factor in the overall thermal management of the device. In other applications, like metal hydrides that are used as hydrogen storage media in fuel cells, the thermal conductivity impacts the kinetics of hydrogen adsorption.
The most common mistake we see in industry is applying a good method of measurement on the wrong type of sample. This is what happens when you're limited to a single tool and are facing a variety of sample formats. The Trident was designed to provide researchers with multiple options on a single instrument platform, so you always have the right tool for the job. It's been a huge success. Leaders like NASA, Adidas, Intel, Kimberly-Clark, Lucid Motors, and universities around the world choose C-Therm analysis tools and the support we provide.
C-Therm customers get access to the most advanced transient methods and are able to test under real-world application conditions, including humidity, temperature, or pressure. C-Therm's patented MTPS single-sided sensor is the fastest and easiest way to measure thermal conductivity. The Flex TPS is brilliant for more challenging applications and testing anisotropic and thin film samples. Our needle probe offers robustness for polymer melts. And the new THW is great for low viscosity fluids like engine coolants.
Not every client's ready to bring testing in-house, so we also offer industry-leading testing services here at Thermal Analysis Labs. C-Therm's highly skilled and experienced team provides access to the most advanced characterization tools for thermal properties and the expertise to make sense of the test results. For example, Rigaku's breakthrough sample observation capabilities allow users to video record a sample as it undergoes a heating cycle. When working with an unfamiliar material, you can see phase changes, crystallization, and other phenomena. This is vital for understanding the material and helping tell the story of how it behaves.
Metrovid's line of DMA offers the broadest frequency range and the highest force available on the market. This is just one of the reasons it is the standard in the rubber and tire industry. We work with a lot of folk developing different fillers for tires, including carbon black. And due to its sensitivity, the DMA is by far the best method to measure the glass transition point.
C-Therm aims to help accelerate material research and improve outcomes driven by better material performance data. Let us help you get the best possible data for your research. Simplifying thermal conductivity.
All right, good day, folks. We'll be getting started with the session here in the next minute or so. Just wanted to do a few housekeeping items before we start the formal session. So just as a note, this webinar will be recorded and available for playback at the end. If for some reason you had to drop off early, or maybe you knew some folks that might be interested but weren't able to make the live time, feel free to share that link for the playback, which will be available after the end of the formal session. I'll also make note that there's a Q&A feature here on the platform. I believe it's on the lower right-hand side of your screen. If you do have any questions throughout the presentation on anything that's presented, or maybe something related to work that you are currently doing, please feel free to type those in. We will be reserving some time at the end of today's session to go over that with you all together. The last part will be, excuse me, my colleague Angad, who is moderating today's session. You'll see him post some different links or resources related to some of the content shown throughout the session as well. So again, just be on the lookout for that. There'll be some different resources and links that you can check out if that's of interest. Okay, so I think we're about 2 minutes past the hour here, so we can go ahead and I'll say jump into it. So go here. So I'd like to formally welcome everyone to today's webinar on exploring methods of measuring the thermal conductivity of TIMs, or thermal interface materials. My name is Arya Hakimian. I'm an application scientist here at C-Therm Technologies. And excited for today's session because we do have, I'll be joined by my colleague, Dr. Genesis Infante, who will also be speaking to some of the aspects of Trident with you guys as well. And we have our special guest, Oliver Roser from ZFW. He's a project manager R&D on thermal measurements. So he'll be joining us to speak a little bit to what ZFW is doing and some of the TIM tester side of material characterization. So should be a nice webinar. Hopefully this will give a nice, well-rounded view of some of the methods that are out there for measuring thermal conductivity in this space. So I'll be kicking things off here. Let's see. So just wanted to start with a little bit of a background introduction to C-Therm for those that may be new to us. Just want to give a quick introduction. So we focus here on C-Therm on the transient class of thermal conductivity measurement. In today's session in particular, myself and Genesis will be describing some of the options available from C-Therm side. But again, these will be focused on the transient measurement systems. So our core instrument platform is called Trident. So you can see a picture of the controller unit here. Trident was developed as a modular platform. So there are a variety of different methods available under one instrument. And really depending on the application, the sample type, your testing conditions of interest, this will largely dictate which method is most appropriate. But again, having the flexibility to pivot into these different options really provides a nice, robust framework for material characterization. And this quote here, it's one that we like to use to really describe the reason behind Trident. So it's a famous quote from Abraham Maslow: "When all you have is a hammer, everything looks like a nail." This is really the idea behind providing multiple paths for testing. There are many excellent methods out there that exist for thermal conductivity characterization. But of course, even the best methods applied on a material or a sample format that it just wasn't designed for isn't going to set you up for success. So being able to take more of a toolbox approach really gives you a nice path forward there in ensuring you're getting the best possible results for your characterization and your research. I will make note of a resource that we do have available as a free download. It's our method selection guide. Again, this is something that's publicly available for free. Excuse me. It gives a nice overview of the different methods available on Trident, but also some of the other methods that are available in industry. If you're maybe new to the space of thermal conductivity testing, or you're just looking maybe to kind of get a refresher on what exists out there, this is a nice resource to take a look at and gives you some information on some of those options that exist. And I will just make note here at kind of the top of the session. So again, we are representing C-Therm Technologies, and that will be the focus of today's talk from my side. But at C-Therm, we do represent both Rigaku and Metrovib in North America for their line of thermal analysis and mechanical analysis testing, respectively. We also have our thermal analysis labs here at C-Therm. This is our contract testing division. So if you did ever maybe need some samples tested, you weren't quite ready to bring an instrument in-house, but you were looking for a testing service, certainly happy to have those discussions as well. So just wanted to mention that for everyone. And the last part of the intro here, always like to end with a client testimonial. We have a variety of testimonials available on our website. You can definitely take a look and see what different folks are saying about their experience working with us and our instrumentation. I picked this one here today. It's a nice, concise, simple testimonial saying the instrument is very user-friendly and training was very effective and productive. This was from Felipe de Souza, who is the Analytical Services Manager at Pittsburgh State University. So always nice to hear what folks are saying about their experiences with us. And again, there's a variety of different testimonials you can certainly go ahead and check out. Okay, so kind of jumping into the main body of the talk here, I wanted to, again, just start at the beginning. What is thermal conductivity? Again, this might be very obvious for many of you, but again, for new folks that may be just getting into this space, I always like to do a little refresher. So thermal conductivity is a material's ability to conduct or transfer heat. You'll see many different data sets and values presented here today. They will all be noted to be in units of watts per meter Kelvin. And again, with thermal conductivity, at a very high level, a high thermal conductivity means you're going to have efficient heat transfer within the material of interest. This is very common for things, on the high end, like metals, for example, typically quite high in thermal conductivity. But there's also a variety of applications where we want to mitigate heat transfer or ensure good insulative performance of your samples. So when you're looking at insulating materials like foams, for example, they will have lower thermal conductivities. And of course, you have the spectrum of everything in between. But at its core, thermal conductivity is an intrinsic material property independent of the size or the shape of the sample. So this is, again, really a fundamental material property that is quite important for a variety of different applications where heat transfer is going to be a critical component of success. Now, going into thermal interface materials in particular, again, just wanted to do a quick high level here. Thermal interface materials, they can take a variety of different formats, whether they're greases, potting compounds, adhesives, etc. But in all cases, TIMs act as this intermediate to improve heat transfer, typically between a heat generating component and a temperature set that is temperature sensitive and the heat dissipating side of things. So the reason TIMs are very critical in many of these applications is even if you have what looks to be very good contact between your two different components of interest, if you really zoom down in, there are going to be these microscopic imperfections, which are going to result in air gaps. Air is a very good insulator. So to ensure effective heat transfer, the thermal interface material is essentially placed in between to help bridge that gap. Now, again, as mentioned in terms of performance metrics here, thermal conductivity is a very important one. You'll look at, for example, a variety of technical data sheets for thermal interface materials, most often within the top, few data points that are mentioned, you will likely see a value for thermal conductivity. It is really a critical performance metric that is used to quantify those samples. But something that I'll be talking about in more detail here, really in my section, is the fillers, because many of these TIMs, what's really doing, I'll say, the heavy lifting and ensuring a specific threshold for thermal conductivity are these additives or these fillers, which are used to tailor that specific performance of interest. And when we are introducing fillers inside of a material, there are some considerations to keep in mind there in terms of the consistency and how that impacts your performance. So one of the big challenges that has really been presented over the years, especially with all of the advancement that is happening with TIMs, is what happens when there is non-uniform dispersion or distribution of these fillers inside of that matrix, whether that's be, those fillers start to agglomerate, they're not uniformly spread, or maybe they're sedimenting towards one side as that material is curing. Again, these are certain issues that can come up, especially in the R&D stages of development, but something that is really important to check throughout that process all the way, of course, to manufacturing and production. So from a material perspective, if you are experiencing these issues, this can result in, of course, uneven heat dissipation, decreasing that overall effective performance. And again, if this is introduced inside of something like a battery pack or, some very temperature sensitive component, it can introduce safety risks, which of course are something we always want to avoid. But then the other side of this is that from a testing perspective, if you're having issues of this kind, this can introduce different measurement bias depending on the method that is used. All methods for thermal conductivity, really any method for any characterization of a material has certain underlying assumptions and requirements that need to be met in order to have a good quality, valid output. And this aspect of inconsistencies in the fillers can, in some cases, introduce some questions or some additional challenges that need to be overcome in order to optimize your material. And of course, when does this show up? Like I said, largely in R&D, I would say this is probably the biggest area that we will be supporting researchers with their testing, but again, also in production. Again, if we just look at like automotive, batteries, electronics, different groups will be looking at thermal conductivity for different reasons. Again, maybe it's developing prototypes, formulation, iteration, even looking at competitor analysis, like taking their samples and comparing and benchmarking QA, QC. This is in many different aspects, this type of measurement can become important. But, your means of verification in an ideal scenario is going to be fast, easy, non-destructive to help you get through what can sometimes be quite a backlog of material testing that needs to get done, right? So again, focusing on the filler side of things, I wanted to introduce our MTPS, Modified Transient Plane Source. So this is one of the methods that is available on the Trident system. As you can see, it's a single-sided sensor design. The active area, just to give you guys an idea of size, if you've never seen the sensor in person, it's about 18 millimeters in diameter. So one of the key requirements here is that we can at least cover the sensor with your material of interest, covering that entire face of the sensor. Now, this is very high level, and I just wanted to give this information again to folks that may be new to the topic, but transient methods have, I'd say, a similar underlying assumption in that the sensor itself, this is acting as our heat source. So the sensor is electrically heated. It's providing this thermal input to our system, to the sample that we're measuring, and we are monitoring the change in temperature as a function of time. And this region here, the transient zone, where that temperature is changing dynamically over that time period, this is where the analysis is occurring. So whether you're looking at, the MTPS or the TPS that my colleague Genesis will talk about in the later portion of the session, they have these underlying kind of, I'd say, similarities. But of course, each method does have some differentiation that is relevant to the specific method. But at a very high level, that's the main idea there. Now, with the MTPS, just wanted to give a little bit of information on kind of sample size requirements. We do have the ability to test quite a range of thermal conductivities with the MTPS, everything from low conductivity aerogels, insulations, to metals. But for TIMs, typically more polymer-based samples, just as a kind of a general benchmark, we need approximately 2 millimeters of material thickness in order to get a good measurement. The nice thing with the MTPS is there is no real maximum size limitation. You could have a larger block, kind of something shown on screen there, and test that just fine. It's nice you don't have to do a lot of sample machining to achieve a very specific format for a good test. It's quite flexible in that regard. We also have the ability to measure non-solids as well. So whether that's liquids, powders, pastes, the MTPS, there is this what's called a liquids and powder cell, very simply fits over the top. You can load that with your sample for measurement. And again, it provides a way to contain that non-solid material for testing. So covers a nice variety, a nice range of material testing options. But again, I really wanted to focus on the filler side of things. And one of the unique testing capabilities of the MTPS is what we call thermal mapping. So looking at this sample here, just we'll use this as our example. We can see very clearly just by looking at it, non-uniform filler has been kind of shown and cured into this material. So this was an epoxy with a conductive metal nanoparticle introduced. But as we can tell, not what I would call the best material. But what we can do to really quantify this is by taking the MTPS, and these circles here are essentially representative of the active area, so the test location that was done. We can place the sensor at these discrete spots and then very quickly get a nice overview or understanding of the either consistency or, in this example, the lack thereof in terms of that thermal conductivity of the material. So it provides a very quick way to go about verifying some of these aspects related to that filler performance. Of course, this is a very exaggerated example. But if the material that you were working with was potentially, opaque in nature, you weren't able to visibly pick up on those issues, the MTPS provides a nice path forward there. And each one of these measurements takes, like start to finish, it's like under a minute. So, this type of assessment here would take just shy of 10 minutes to have that full kind of coverage of the material there. So the last one, again, another example here where we take, the MTPS measuring at different locations. We can see we're getting some differences in output here, again, related to that filler inconsistency. But again, this is with the MTPS. But I just wanted to share one of the reasons, again, why this can be important, because my colleague Genesis will talk about this in further detail here. But if we take this same sample and then measure it on something like the TPS method, well, we can see that this value here is somewhere in between the lowest and highest value that we showed on the MTPS spot measurements. And it's important to keep that in mind because some of these methods will essentially average out over a larger area. The MTPS has a controlled directionality to it, so we're getting this kind of more pinpoint measurement location. Some methods, again, will have different evaluated volumes, and this is something, again, Genesis will go into a little bit further here, but it's just important to understand that when your materials are potentially non-consistent or have these issues present, this is where you can start to see some differences in the output. And which one is correct? Well, it really depends on, of course, what are we looking at here? Because this is essentially averaging out over a larger area, where these MTPS are more spot tests. So different groups will have different levels of scrutiny in terms of how much consistency is required within their material for an application. But again, what you can get out of these measurements is just that additional insight to help really, guide your development and make sure that your materials are acting as you are hoping they will and hitting those performance metrics that are required. So I'm just going to end my section here by saying if this mapping and kind of the assessment of the filler is of interest, we do have a variety of previous webinars done specifically on this topic. I've flagged 2 here, and these are something that you can find on our website. But thermal mapping for improved molding processes, this was actually done with a guest speaker from Synergy, a group in the UK. And then there is another really nice one that was done on high thermally conductive solutions for automotive applications. And this was done in conjunction with Von Roll. So if these topics are of interest, there are certainly some additional resources that you could go take a look at. But from my side, I'll go ahead and stop sharing this at this point, and I'll leave it to my colleague Genesis to take it from here. So thank you, everyone.
Hello, everyone. So I'll be taking over for this portion of the webinar. I'll be talking about the TPS technique, or the transient plane source, and kind of like a contrasting technique that is also available in our Trident system. So shown right here are the different types or sizes of the TPS sensors that are available for our system. It is a double-sided sensor with a bifiller spiral active region right here as a sensing part. It's very thin. It's encapsulated by Kapton material as an insulator, with that insulating the active nickel foil that is basically the sensor portion of the whole instrument. So covering just the, before proceeding with the materials, the testings that we've done in terms of thermal interface materials with the TPS, I would like to just cover the basic principles of operations on how the TPS operates in general. So it is, as I mentioned, the TPS is a very thin sensor, approximately 150 to a 200 micron thick total. It is, as I also mentioned, it is double-sided, designed for that symmetry between top and bottom. And the general idea is that you'll basically surround the sensor with your sample. So in this case, for the TPS, you'll have to sandwich that between 2 flat and smooth surfaces to really maximize that contact between the sensor and the material. So the general idea procedure here is that it's very similar to any non-transient methods where the sensor itself is also the heat source, meaning the Trident or the controller inputs a known amount of current into the sensor heater. That heat is being produced from the heater and then transfers into the sample itself. And then, all of that is dictated by the operator itself, adjusting conditions such as power levels, amount of testing times, which all depends on the type of sensor that you'll be using on top of it. So it's a little bit more engaging in terms of operating it compared to something like the MTPS, for example. But all of that will be covered essentially by training and according to guidelines provided by the ISO standards, which I'll be also discussing in a little bit. So as the heat transfers from the sensor to the material, we monitor that change in temperature over time, so the delta T, and that's basically the output of your analysis right here. Depending on the materials you're testing, whether that's highly conductive materials like metals or more in the insulative side of things like polymers and insulations, the time it takes for a valid test can vary by quite a bit. So, and it's all a function of how the TPS really works and the fundamental level, which also I'll be covering in a bit. After all that output with the delta T versus time, you can extract the thermal properties such as the thermal diffusivity and thermal conductivity directly from the material through an iterative process built in within the software. And all of that process really, again, is really mathematically and all are all covered in the ISO standards, which we'll be presenting right here. So very important for the TPS, and I think this is the biggest value for the method itself, is that a lot of people like the fact that there is an ISO standard, the ISO 22007-2, that completely covers and describes the transient plane source as the method in measuring, polymers, insulations, metals, all types of materials, and what people really value from it is that it is the association of that standard can be very valuable in technical data sheets, for example. It is generally designed to test solid samples, so bulk, varying from sizes like bulk and thin materials, depending on the testing that you want to do, depending on the context of applications, directionality, and all of that. But for the context of this discussion, we'll be only covering certain aspects of that application. There's also options for testing at really low temperature, cryogenic, for example, -200 liquid nitrogen temperature, all due to high temperatures from 300 degrees C max to maybe 600 to 700 degrees C max, depending on the configuration and, again, the needs of your testing. So coming in with the what we call the standard TPS utility is what we call the bulk utility. The TPS has been originally designed to measure materials that are in bulk configuration. What that means is that there is a certain thickness and width, length and width, or diameter associated with it, and again, requirements really that needs to be met for a valid TPS measurements to happen. And what that means is that this dimensions of this bulk samples must meet the minimum requirements as described in the ISO. And that effectively is a function of the thermal diffusivity of the material, the test time, and essentially, and finally, the diameter of the sensor. So as kind of like a quick guideline, not to overly complicate it, basically what you need is that in a bulk testing, you will need a thickness of at least equal to the diameter of the sensor used. So it could be 6, 13, or 30 millimeter, for example, or greater than the diameter. And as for the diameter of the sample itself, it has to be greater than or equal to at least the 2.5 times the diameter of the sensor. And all of this requirement really boils down to how the TPS functions. So if you can imagine, you have the TPS sensor layer with the top and the bottom sandwiching the sensor, and then you maximize the contact by clamping it, the stack. How the heat flux propagate within the material is very important. So for the bulk utility, the certain assumptions right here is that the heat propagates in a equally in all directions. So if you can break it down to different axes, so Z, X, and Y plane, you assume that the heat flux propagate equally in the same rate all throughout in that space. So you can visually look at it as like a bubble spreading within the material as the testing is happening during the test time. And the underlying assumption in that math is that that heat flux bubble during the test does not hit any boundaries within the material itself. So the assumption is that the heat flux propagates within a semi-infinite media. And if that assumption is not met, there is certain biases and error associated with that when it comes to your final product or results in thermal conductivity and diffusivity. So it's very important that we follow that guideline as close as possible. And that these are usually just the minimum requirement, and then the larger the sample, the better it is in general. So going into the specific applications for thermal interface materials, what we have here is a silicone gap filler. So gap pad, specifically the C-Therm SC1200, measured using the TPS from our TPS Trident Flex TPS right here. And the TDS reports that they also did measurement using similar technique, the hot disk transient method technique, which is interchangeable between TPS and hot disk, is pretty much the same thing. They measured about 2 watts per meter Kelvin. From our measurements, you can see here that it is very repeatable. You can see that there's different batches of testing. And you can see that the TPS was successfully able to match whatever the TDS has reported, which is great, which is what you want to do if you purchase a silicone. You want to make sure that whatever the TDS is reporting is as accurate as possible. And what we have here then is a comparison of methods between the MTPS, which my colleague Arya just covered earlier, and the average value for the TPS. And you can see that there is for the most part, it's a good agreement between two methods. But again, only when samples are really consistent. So what that means is that there is a certain different conditions that these tests are being done depending on the method. And in this case, it's great that between the two different methods, the values are agreeing with one another. So what I mean by that is that, often enough we encounter, there's different ways that we can measure thermal conductivity out there. There are available both commercially and in literature or like in a research-based level. And depending on those methods, depending on what they do or how they do it, there can be some biases into your value. So really what you can break it down to is that you have to be aware of what type of materials are you measuring? Is it compressible? Is it porous? Is it bulk? Is it thin? Is it a paste? Is it a liquid? So all that kind of can really factor in on the the effective methods that can hone in into the accurate thermal conductivity measurement as much as possible. What's also important to really what people maybe not notice sometimes is that directionality can also be important. So certain methods, for example, the TPS, in a bulk utility measures thermal conductivity as an average in all direction. So it covers that three-dimensional space, and whatever you measure represents that the average of that three-dimensional space. But depending on whether you're only interested with the out of plane or in plane direction, different methods can have some variability on your final results right there. And of course, evaluated volume can also be a very key component to it. So in terms of, let's say, TIM testing, TIMs in general, there is an assumption that within the evaluated volume, you can assume that maybe this particular small part of the TIMs that you're testing is a representative of the whole bulk, right? And maybe having, especially having that assumption can really affect how you interpret the data at the end of the day. And it is important to really evaluate, maybe you're just evaluating a small portion of your sample, of your material, or you're going to have to proceed to go ahead and have more broader representation of the material itself. And again, different methods have different assumptions. For example, contact resistances, compression, defects within the materials or lack of defects in the materials. All of that really adds up on the final results of your thermal conductivity testing. And I think most importantly is the conditions and the setup. This is very important for TIMs, from what we can observe really, is that depending on the type of TIMs that you used, especially if you want to reflect what the user condition should look like, something like compressed state versus non-compressed state, it's really important that your testing really reflects that particular aspect of it. So shown right here is essentially the thermal conductivity of another silicone-based gap filler. In this case, it's relatively high conductive. It's about 10.5 based on the ISO 22007-2 measurement method. And you can see here that we also accessed this specific gap filler and done our own measurements. With this data right here, just looking at the TDS, no one's really specifying on how much of the compression state have been done to measure this this value of 10.5 watts per meter Kelvin. But then, having understanding of compressed states, for example, you can see that there is a variability of that value in terms of thermal conductivity. So based on that, you can see that there's a trend of an increase in thermal conductivity based on the compression on the thermal interface materials. So kind of very quickly, summary and takeaway from my side, and kind of closing in from the MTPS talk earlier. We have the verifying the filler consistency in TIMs really is very important when it comes to evaluating the performance of your materials and, again, testing perspectives. MTPS really provides that quick and straightforward way to really confirm uniformity and dispersion of your fillers. And TPS has been really widely known in the industry. It's basically industry standard when it comes to technical data sheet testing. And again, multi-method testing approach can really understanding the pros and cons between the methods. You can use that to leverage different benefits and non-benefits, I guess, that can have bias into it. And of course, once you have you see a value in the TDS, make sure that you trust it, but make sure you also verify it. So from here on, I'm gonna pass the floor to Oliver Roser from ZFW, and he'll be covering the more information about the D5470 TIM tester method.
Yeah, thanks, Genesis, for the kind introduction. And of course, thanks to C-Therm for inviting me to present at today's webinar. Yeah, after the guys from C-Therm covered some really interesting facts about transient methods, I will continue with a talk on the steady-state cylinder method according to the ASTM D5470 for measuring thermal conductivity of thermal interface materials. But before I start, let me briefly introduce ZFW. ZFW is a German abbreviation for Zentrum für Wärmemanagement. Translated to English would be something like Center for Thermal Management. And we are a research and development service provider related to thermal management in electronics. This includes general consulting, system design, validations, but also thermal simulations, material characterizations, and so on. And a big focus for us is, of course, thermal interface materials. And over the years, we developed some specialist devices for measuring and testing thermal interface materials for a variety of properties. And the TIM tester, which I will present today, is one and the first device we developed for this purpose. Yeah, thermal interface materials, I already introduced the purpose, are available in several types. So there are thermal greases, gap fillers, thermal pads, thin films, graphite layers, even to liquid metal materials. And of course, it's challenging to find methods that deliver comparable thermal conductivity values for all those different types of materials and for best under application-related boundary conditions. And therefore, not only the transient techniques, but also the steady-state cylinder technique is pretty much suited. Let me first introduce the standard, which is now online for a long time. So the first version came out in 1995. And we today have the actual version from 2017, the ASTM D5470, which is called Standard Test Method for Thermal Transmission Properties of Thermally Conductive Electrical Insulating Materials. A long title, but it's just saying we measure different properties such as thermal resistance, or sometimes also called thermal impedance, thermal conductivity, and also thermal contact resistances. And that makes the steady-state cylinder method very interesting for the use of thermal interface materials. I just put those quantities with their units there because I go a little bit more into detail in my next slide. So when I refer to a small r, then we're talking about thermal resistance. K or lambda will be thermal conductivity. Thermal resistance typically specified per unit area, so it's square millimeter Kelvin per watt to avoid the area dependency. And according to the standard, it can be used for several material classes, typically 3 classes: viscous liquids, viscoelastic solids, and elastic solids. And when we just name a few examples, we can start with the very thin liquids, starting from water, for example, and going up to the rigid solids, ceramics or metals. And the thermal interface materials are typically somewhere in between, typical thermal grease and pad materials or viscoelastic cured gap filler materials. Okay, one slide back to theory, discussing a little bit what are the basics of the steady-state cylinder method, because they are pretty intuitive and straightforward. So it's interesting to see that before we talk about the device and how it works. What is the idea behind? So we have a sample, and the sample conducts heat, and within the sample, the heat conduction can be described by Fourier's law in 3 dimensions or simplified in 1 dimension. And it just tells us that the heat flux conducted through the material is proportional to the temperature gradient applied, and the constant of proportionality is thermal conductivity K. And to find out what is K, thermal conductivity of the sample, we need to somehow excite the sample thermally and then look at the response. What Arya and Genesis already introduced. There are several techniques, several thermal signals we can apply to the sample. For example, in the laser flash principle, we have a pulse excitation. We just take a heat pulse, excite the sample, and take a look at the temperature rise versus time. So the method the guys from C-Therm introduced work with something like a step function. So we apply a heat flux from a certain time, keep it constant, and take a look at the temperature rise. And what they are evaluating is the transient zone, so the increase in temperature. There are also other methods using an oscillating signal, a periodic signal, exciting the sample and checking the result. And what makes the steady-state cylinder method such special is that we are not checking a signal versus time, but just a thermal equilibrium. We send a constant heat flux through the sample, which is independent on time, after, of course, it equilibrated, and then we are measuring the temperature gradient across the sample. And from those two, we can directly evaluate with Fourier's law the thermal conductivity of the sample. So how is this done? We have a typically disc-shaped sample. It is inserted between 2 metallic meter bars, an upper meter bar and a lower meter bar. The upper is heated, the lower is cooled, and we send a one-dimensional heat flux Q set through the sample. And then we evaluate the temperature gradient across the sample. And when we have it in a one-dimensional manner, it's just a temperature drop across a sample of thickness D. And to measure this temperature drop, we insert 4 thermocouples in each meter bar, measure the temperatures, 4 temperatures in each meter bar, and then make a linear regression across these temperatures. So to approximate the temperature curve across this meter bars, extrapolate to the sample surface, and then we directly have the temperature drop from the upper sample surface to the lower sample surface. And of course, measuring thickness is pretty straightforward. There are different methods available. I will show you later how it is done in the ZFW TIM tester, but it's pretty intuitive. Measuring the temperature at the surfaces of the sample without touching the samples is much more challenging, and therefore we need this extrapolation method. Yeah, and from the temperature gradient caused by this heat flux, we can directly evaluate thermal conductivity or thermal resistance. But what we need is, of course, a measure of this heat flux we sent through the sample. And in a simplified way, we could, for example, use the electrical power used to heat it up on the top side. But to make it a little bit more accurate and to make more precise measurements, we use the linear regression of temperatures within the meter bars to determine the heat flux. And this is done by evaluating the temperature slope or temperature curve slope in the upper cylinder and the lower cylinder. And what is pretty intuitive, in the upper cylinder, we have a slightly higher heat flux than in the lower because we have ambient heat losses in between. And now to evaluate the heat flux within our sample, we need the average. To calculate the heat flux in each cylinder, we just need to know what is the thermal conductivity of the material it is fabricated from. And this can be a copper, stainless steel, or in our case, typically aluminum. And we precisely know this aluminum thermal conductivity, so we can calculate the heat fluxes in the upper and the lower bar. Build the average, and then we have our measuring quantity. And that's it. So while the transient methods are very complicated in math and in the idea behind and in evaluating the temperature field, the steady state method is pretty intuitive, applying a heat flux and measuring the temperature gradient. Okay, and that's how we build our apparatus. There are some pictures. We'll go a little bit into the details on the next slide. You see it on the right upper side. It's a tabletop device consisting of a measuring chamber and a control unit. Within the measuring chamber, we have the main measuring section. This is the upper bar, what you see here. That's the lower bar here. And then we have a lot of secondary devices around it, which I will introduce on the next slides. So the upper copper part is heated and the lower copper part is cooled. And this is the direct measuring section. And then the zoom in picture down in the right, you see it directly with a sample. The green material is a typical automotive gap filler for battery applications. Okay, let's go a little bit into the details. Big benefit of this method is that we have application-relevant boundary conditions during the measurement because the material is clamped between 2 plane parallel surfaces as it is used in the real application, between a chip and a heatsink, for example. And then one side is heated up, the other is cooled. It's the same as in the application. In our device, we have a diameter of 30 millimeters of those meter bars, so the samples are also with a diameter of 30 millimeters. We can heat up the upper side up to 180 degrees, cool down the lower side to 5 degrees, and then we have mean sample temperatures for measurement between 10 and 150 degrees. To really measure precisely and get accurate results, we need to measure temperatures at very well-defined points within those meter bars. And that requires that we have very small thermocouples or temperature sensors. And our thermocouples are calibrated to 0.01 Kelvin absolute accuracy and have a small diameter of just 0.35 millimeters, which lets us measure really a point temperature within this meter bar for higher accuracy. We need to measure the thickness of the sample as well, or the gap width. We do that in a contactless manner to eliminate any parasitic heat paths, because we would if you have some mechanical device around the sample, we would have a parallel heat path, and that is very difficult to compensate in measurement. We also reduce thermal expansion effects by just measuring contactless and optical with a precise LED micrometer. We can measure sample thicknesses in the device up to 10 millimeters with a high resolution smaller than a micron and an absolute accuracy in the typical range of 4 microns. And let's take a look at the mechanical side. We have a floating mounting in the upper cylinder to compensate for surface irregularities and non-parallelity in rigid samples. So if you have a solid sample and the surfaces are not perfectly parallel, you need to somehow compensate for a misalignment, and therefore we have floating mounting in the upper cylinder. We have an electrohydraulic lifting unit for precise gap and force control and can apply surface pressure up to 2 megapascal with this device. And for different testing, different special applications, I will introduce a few at the end of my talk. We have multiple motion sets for automated testing, for example, cyclic loading or defined pressure steps, defined gap width that can be carried out step by step during measurement. Okay, before we go a little bit more into details, what we can measure, I need to mention a very important fact that I missed on my first slide in the general introduction. When measuring thermal conductivity with a steady state cylinder method, we clamp the sample between 2 aluminum bars, and the thermal resistance we can measure, or even the conductivity, is not just depending on the material's bulk, it's also depending on the contact towards those metallic meter bars. So we have some contact resistances included, and when we build up a resistance chain, we just need to sum up the contact resistances and the bulk resistance and have a total resistance. In the ASTM standard, it's called thermal impedance. And when we convert that to thermal conductivity, it's just apparent thermal conductivity that contains the effect of the contact resistances. Of course, there's a solution to really extract and isolate bulk thermal conductivity and contact resistances. And therefore, we need to perform measurements at different layer thicknesses. What you see here is a typical example of thermal grease, specific thermal resistance measured as a function of the sample thickness. 0.2, 0.4, 0.6, 0.8, and 1 millimeter. So different sample thicknesses. And afterwards, we can perform a linear regression through the results. And the slope of this curve is the inverse of the bulk thermal conductivity. And when we extrapolate to a zero gap thickness or a zero sample thickness, then we just get the remaining part of contact resistances. So that's, of course, a theoretical assumption that when we lower the thickness of the sample, and when we reach zero, when there's no sample in between, then there's just the contact resistance remaining. And that's the way how we can extract those two values, which is very important for thermal interface material applications to know both. And this slide just collects the typical ways how to measure thermal interface materials. On the upper side, you see measurement results as a function of the gap width. And on the lower side of the slide, you see the measurement results depending on the surface pressure. On the left side, always the thermal resistance. On the right side, the thermal conductivity. So the left upper side is what you have already seen. Thermal resistance increases linearly with sample thickness. When we convert that to thermal conductivity, we see that this is almost stable for high sample thicknesses, but for low sample thicknesses, it drops significantly because the contact resistances become more important when the layer thickness decreases. When a thermal grease is applied, we often use a pressure-dependent measurement and not a constant gap measurement. And what we gain then is the decreasing curve of thermal resistance with surface pressure. And in this case, for example, decreasing thermal resistance from 7.5 down to 2.3 square millimeter Kelvin per watts when reaching the 2 megapascal. And when we convert that to thermal conductivity again, we get an increasing value with surface pressure, which is due to the particles pressed together, pressed to the surface of the substrates of the meter bars and percolation, which is achieved. Okay, and before switching now to some special applications, one last slide, which is very important to note, accuracy of the method, uncertainties of the method. And this is pretty easy to capture here. We have a well-defined measuring area where we have roughly 6% of uncertainty. And this is from a very low resistance of 50 square millimeter Kelvin per watt up to 30,000 square millimeter Kelvin per watt. And just when exceeding those limits, then the uncertainty decreases because for example, the temperature drop gets so small that the accuracy in temperature measurement is not sufficient anymore. Or the other case, when the resistance is that high that the heat flux through the material decreases, then the environmental heat losses increase and become more important. But there's also a workaround for those areas. Then you need to adjust the temperatures, you need to adjust the meter bar material, and so on. But there's a very wide range of high accuracy of down to 6% in absolute accuracy. Okay, and now as introduced and already told previously to the webinar, that we will show some special applications, how we can use this TIM tester beyond the standard of just measuring thermal conductivity according to the ASTM standard. And for example, we do delamination testing. We compare materials due to in terms of their adherence properties to those meter bars. In the upper example, you see a very soft and tacky thermal interface material, and in the lower pictures, you see a very stiff material. And what we do is oscillatingly moving those meter bars with 20% of expansion, very slowly, 5 microns per second, just to imitate the thermal expansion during the usage of the electronic device. And what you see in those charts now is the tracking of the gap width, that's the D, the black curve, the first force that it's needed, that's the red curve, and the change in thermal resistance at the same time. And while the upper material adheres very well to the cylinders, and where the thermal resistance changes just insignificantly, we have a delamination effect on the very stiff material. And at roughly 20 seconds after testing, you see a delamination, you see the crack, the force breaks down, and what you see is an increase in thermal resistance of 340%. And that's a very nice method to compare those materials, to compare their adhesion properties to solids, and also to analyze the effect of a delamination on the overall thermal resistance, which is of course not covered in the standard, but what is a very nice application of the method. Of course, if you want to go a little bit deeper into the contact resistance topic, then we ask the question of how can we adjust the surface structures of the meter bars? And there are two options for us. Of course, for extensive studies, we are able to exchange those meter bars in different materials, different surface structures, different sizes. But for the fast measurements, we typically use those disc-shaped substrate samples, which we use for building up multi-layer samples, as you see in the lower example here. And we can really individually adjust those surface properties, rough surfaces, polished surfaces, coated surfaces, to check the combination with different thermal interface materials and measure then thermal contact resistances. Also very interesting, checking or tracking the melting process of a phase change material. What you see here is the black curve, decrease in resistance during the melting over time of a phase change material, and the red curve shows the temperature increase. So we put the material between the meter bars, increase the temperature from roughly 30 degrees up to 60 degrees over, let's say, 15 minutes. And what you see is a reduction in thermal resistance of about 80%. Then you can nicely track the melting process and the process of the phase change material penetrating the surface cavities of your substrates of the meter bars, for example. And last but not least, a method that we developed during the last years, including microthermography to the TIM tester device, to the steady state cylinder method. We apply a very high resolution microscopic infrared camera to measure temperature difference directly at the surface of the samples, which can be used for very small samples, as you see here. So these are the typical meter bars on the upper and the lower side, and we have just a 3 × 3 millimeter sample, and we want to measure temperature gradients across this sample. Then we can do that with the microthermography. Or it can be used to analyze local thermal resistances in thin layers of such a multi-layer sample. So what you see below here is a thermal resistance curve measured using microthermography across this multi-layer sample. You have almost no resistance contribution in the substrates, linear increase in the bulk, and then you have those contact zones that can be, for the first time, really extracted from those results using the TIM tester combined with microthermography. Also very interesting and special application. Okay, let me summarize that. Let me summarize the main features of the TIM tester I introduced. So we are measuring thermal resistances, impedances, conductivity, contact resistances of different types of materials. Liquids, greases, paste, solids, thin films, almost no limitations. Sample dimensions in a standard configuration, 30 millimeters in diameter, 10 microns up to 10 millimeters. With a resolution lower than 1 square millimeter Kelvin per watt in resistance at sample temperatures 10 to 150 degrees and with a surface pressure up to 2 megapascal. Yeah, and that's it. If you are interested in learning more about us, just use the first QR code. If you are interested in more information about TIMTester, use the second QR code, or just contact one of my colleagues or myself, and we are happy to receive your request for further details for measuring your materials, or even if you're interested in buying one of those devices. And with that, thank you for your attention. Thank C-Therm again for inviting me, and hand back to Arya.
Awesome. Thank you very much, Oliver. So yeah, I know we're at the top of the hour here, folks. I'm just going to very quickly go into a little bit of an outro for today's session. So I'll get this up on screen. You know, if this was interesting to you, and again, maybe you wanted to look at some previous webinars or technical resources, we do have a variety of those available on our C-Therm website. Definitely feel free to check that out. I will just make a note of some upcoming webinars that may be of interest to folks. Over the month of July, we do have 3 where we'll be taking a look at some STA applications, thermal conductivity and thermal analysis of MOFs for carbon capture, and then a focus on specific DSC applications towards the end of the month. We're also going to be at some upcoming events. If we happen to be, in your area, or you might be attending some of these, we'd love to have a chat. The Advanced Materials Show, which is happening in the UK, July 9th to 10th. Battery Show Asia, which is happening in Hong Kong, July 15th to 17th. And we will be actually hosting a Innovations Day in Houston, Texas on July 24th. This Innovation Day in Texas will be covering both C-Therm's thermal conductivity instrumentation, as well as our Rigaku thermal analysis. We're also going to be there with Rigaku's XRD group and green imaging, which is focused on some specific geological applications. So it'll be a nice event. If you're in the Houston area, definitely feel free to check that out. And generally, if you'd like to learn more, maybe, look a little more detail in terms of what you're working on, how these solutions could be a fit for your research, we're always happy to schedule a technical consultation, do a little bit more of a specific deep dive. But if you're just looking for some general quoting information, some costing, or to look at our contract testing services, again, these links will be posted in the chat. Definitely feel free to reach out for any inquiries in that regard. I'll plug our LinkedIn here. Give us a follow if you're not already doing so. This is where you'll get all the latest up-to-date information on upcoming events, content pieces, etc. And with that, we'll wrap things up and close out today's session. For those that are interested, I know there's a couple questions, so we will go into those into the Q&A in the next minute or two if you're able to stay on the line for a few more minutes. If not, and you have to drop off at this point, I would just like to once again echo myself, Genesis, and Oliver's gratitude for you guys all joining and participating in today's session. I do also want to specifically thank Oliver for joining us today. Really interesting content on the TIMTester and the work that ZFW is doing. So very thankful for you for joining us here in today's webinar. So with that, we'll go ahead and end the formal recording at this point. Again, for those that are available to stay on the line for the Q&A, please feel free to do so. Thanks, everyone.